There we are. Cool, recording started, and we'll start with, of course, the classic, very exciting administration stuff that everyone loves. So we'll start with the attendance form. I'll grab that and paste that into both our Google Meet and our Discord. Obviously just fill in your name there, let me know you're rolling around. I sense the attendance might drop off as we get closer to the end of the year because people get very busy, but we'll keep track of things. You two can set some records. And then also, on the topic of the AGM, since just about all of our committee is either leaving university next year or will be too tied up with projects, we'll need people to run the society. But with that being said, even the people who are graduating will probably be around to give plenty of guidance. There's obviously this handover period here, and more. You can always, message people online. We still keep in touch with some committee members that have graduated like 2 or 3 years ago, and they help us out from time to time. So don't worry if you're not too terribly experienced. All you really need to do is be eager. So I'll grab that AGM interest form. I think, to be honest, you guys might have already filled it in. But in case you haven't, if you know someone who would like to run the society with you or something like that, you can send them that. That's just the interest form. It's obviously non-binding, but the AGM is next week, and it'll be right after the bootcamp session then. Cool. Only other thing is, I think, in fact, I got a message about a couple seconds ago. Nice. Yes, so it looks like, I've just confirmed now, that next week's bootcamp session and the one after that will probably be more advanced CAD topics back in Fusion 360, and I won't be running those personally, which will be wild because I have run all of them so far, but we'll actually be dragging in Peter, who is on the committee of the CAD Society, so he's quite experienced in these things, and he'll be going over some much more advanced Fusion 360 topics that I didn't get a chance to cover when I was doing the basics last semester, and the beginning of the semester, sorta, with the 3D printing thing. Cool. That's admin-y things and plans out of the way. I guess that leaves us with picking up on our project. So, just to refresh our memories, I guess, I'm pretty sure this is the right one. Last time we were around, we managed to put together this schematic. And I realized today that the interface of things might be a bit small. I've tried quite a bit to get KiCad to scale up properly, but it remains stubbornly small. So I'll be sure whenever I'm pointing at tiny things to read it out verbally as well what I'm clicking on. But at least we can zoom into the actual schematic part of things. Cool, and of course just let me know if you are ever missing anything, can't see it, just send me a message in either of the chats. Awesome. So here's where we were at last time. We were making a tiny little development board, a little bit like in Arduino, but a tinier version with this processor here. So this is the microcontroller itself. We've connected a whole bunch of just input-output pins to it, so there's GPIOs. That would be the pins that you'd be like putting into the breadboard or whatever. We slapped an LED on it, so we can play with that. This capacitor here is for decoupling things. So I sent around, or there were some links included, I guess, in last week's write-up, or, well, more than last session's write-up, about these decoupling capacitors. Basic idea is they smooth out the power going to a chip to prevent it from doing anything squirrely. So we'll have to make sure when we're actually setting up our PCB that this capacitor 1, is as close as possible to this microcontroller. Reset switch, obviously, that's just pulling this reset line low, resetting things by connecting it to ground. There's the pull-up resistor, so that pulls it up when this button is not pressed. Here's our battery connector. These power flags, remember, were just there for getting this rules check to play nicely. So you see if we run that, we get no errors, which is nice. Without these, I'll just say demonstration. Can I kill one? There we are. And then if we run this, it'll complain. Aha! It's not driven by anything. That just means it doesn't know that this pin, this power input, is actually an input. Because we've named this pin connector here like battery, but it doesn't know that that's a battery, I guess. Cool, there's that. Here's our voltage regulator. We followed the schematic for setting this up, just a couple of decoupling capacitors. It's a linear regulator, turns excess energy into heat and gives us 3.3 volts out of whatever our battery is, as long as it's more than 3.3. Awesome, that's that summarized. There's our programming header. So basically, what we're going to do now is take this schematic and turn it into an actual physical PCB. So today we're doing the physical design part of things. If you'll recall as well, the last thing I think we did, this might have been a bit rushed at the end. I got feedback that last session was a bit quick, and I would agree with that, actually. But yeah, so this is a little tiny, for which I apologize probably. But the idea is that here is our list of different symbols. So this one up here says like C1, C2, C3. So those are our 3 different capacitors, 3, 2, and 1 over here. And in fact, I can make this a tinier window in front of the other window, can't I? Yes. Ooh, very fast moving computer. Only the best performance for us. Okay. Yeah, so you can't quite see what's behind there, but that's all right. So you see these. Remember last time we went and picked out those footprints by looking at the website. Or I think we looked at RS components to see what size we could buy capacitors in, for example. So 0805 is the shape of all of our capacitors and resistors, for example. And our button switch has its own shape. So all of these physical shapes, footprints, we assigned last week, well, last session. And today, we're going to see them on a board. So, to see them on a board, that was, I guess, just to reacquaint ourselves before I jump onto the PCB part. Oh, you remember now. Yes. Yeah, the footprint part's always the roughest bit. Yes, definitely tedious work, the footprint part. But, after looking through all the data sheet and all that digging around last week, I think we've gotten to the, well, almost less tedious part. For this tiny board, it'll be pretty easy. For bigger boards, it can also be tedious, but I guess that's just electronics for you. Before I fly on to actually putting all these things on a PCB, are there any questions about where we were last time around? Or anything here in the schematic, or how this footprint thing works? Because I'd be happy to answer those, if there are any. Oops, that's not even the right thing. Exciting. Cool. Okay. Excellent. No questions thus far. Obviously type any if you have them. But I think then we'll go and take a look at designing a PCB. So, there's our schematic. Lovely. Now that we have that fully made, we can just close that window. I don't know what changes I made, so I'm not going to save them. And from here, what KiCad is actually a collection of different like mini programs. So we were just in eSchema, which is the schematic editor, but there's also an editor called PCB New for making actual PCBs. So if you click on PCB Layout Editor while you're in your project or whatever, that will take you to a totally different looking program. Well, okay, somewhat different looking program. But things are all tied together. And I realize this is probably going to be really interesting to see on a stream and recording, especially because it's such a dark background with a very tiny grid, but that's right, we'll zoom in once we can. So first step to do is we need, on this giant blank piece of page, to bring in all of our parts. There is luckily an easy way to do that. There are a couple of different ways to do this. You can generate something called a netlist, for example. So the last program we were in, the schematic editing one, has something for exporting netlists, and this has something for importing netlists. But luckily there's something even easier. If you just go over to Tools, which is this tab here, it says Tools, and then if you go down, there's one option that says Update PCB from Schematic. So that will update this current PCB design from the schematic. So I click that, pops up this menu here. Default settings are totally fine. Smash the Update PCB button, and then close. And in here, you'll see attached to my mouse is this little blob of things. It's very small looking. And that is, or those are, rather, all of our footprints. All in a lovely, disgusting mess. So, you might recognize, well, maybe recognize, and they're actually labeled decently. So here, for example, I'll click off of that. Here, for example, is our battery connector. Here are some resistors and capacitors and LEDs, all of which are 0805, I think, in terms of their footprint. Here's our linear regulator, so that's our power. Our massive, oops, I didn't want to do that. Our very massive power switch, or reset switch even. Here are the nice little 4-pin GPIO things. So this is how we'll connect up like our Arduino-y thing to it. Well, sorry, that doesn't make any sense. This is how you would connect anything to it like an Arduino. So, for example, you'd stick these maybe in a breadboard. These little holes you could solder those standoff spiky pins into. You could put it in a breadboard. And obviously here's our processor in the middle, microcontroller. So, with that all plopped onto the board, we need to figure out how to arrange it. So actually, I think the first thing we'll want to do is design the shape of our board itself. So when it comes to, well, there are a couple of ways to do that, I guess. Your PCB obviously needs to have a physical shape, like in the real world, because we've now switched from doing schematics, which are purely in the electrical, like kind of theoretical almost world, to now things need to be physically manufacturable. So at some point you need to say, well, what does this board actually look like? The shape of the thing that will come like in the mail or the post. So to do that, there are a couple of ways of doing it. You could, for example, go to this edge cuts layer. So there's a layer over here that says edge.cuts, and that layer is what stores the boundaries of your PCB board. There are a couple of little tools built into PCB New for drawing things here. Like over here you have add graphic lines is what that one says, or you could add a graphic circle or an arc, or even a polygon there. So just as an example of one way you could do this, you could jump into your grid, say, this is like your snapping almost, and you can scroll up to here. This one says grid 1 millimeter, so this means my mouse moves in 1 millimeter increments. At least the little cursor behind it does. So when we draw a rectangle, you'll be able to see that. If we do something up here and go down, you can see it kind of snaps, which is really convenient. It helps you be a bit more precise than you could otherwise. And you could do just something like this, where you draw around a rectangle and then click back where you started. And you filled something in, and this is on the edge cuts layer. You can toggle that visibility on and off with that little checkbox there. The issue with this is it's somewhat difficult to be precise if you need to be with the shape of your PCB. For example, if we wanted to add things like screw holes, we'd have to either be eyeballing it or relying on this grid snapping to put them in the right place. So it's not necessarily the most robust solution in the world, I guess. Luckily for us, we can use a bunch of other programs, CAD programs that are actually designed for this kind of precision to generate a 2D shape, export it as a DXF file, and then import it into here. So that's actually what we'll be doing today, just to show off that. Now, I will also be following along with what I think at some point I mentioned. This is based on a tutorial on GitHub called the Hawk PCB design tutorial. That'll be in our links for today. But he shows off there a really kind of neat CAD program, and so I'll show it off as well, just to raise some awareness for it. But as a disclaimer before I do that, if you are more comfortable, for example, with Fusion 360, I don't have Fusion 360 on Linux, otherwise I'd probably use it, then definitely use that. Any CAD program that you can design 2D shapes with is good to go. But I will show you one that's very different from the rest of, I guess, CAD programs that you might have come across before. This one is called Openscad. I will first actually find you a little website link, just in case you're interested. You don't need to download it, especially if you have like Fusion 360 on you. But I'll fire it off things in case you're interested. I'm mostly keeping it to the meeting chat today instead of the Discord one because, I don't know, you both seem to participate in the meeting one, so might as well just leave it there. And only paste things in one place. But, yes, Openscad. So, et voila. Here's kind of what it looks like. I'll zoom in on that page for you a little bit. In fact, I'll zoom in on, yeah, I'll just zoom in a bit on this page. You can see it's the Programmers Cad Modeler. This one's interesting because you describe things programmatically, which is quite intriguing. So if you happen to like writing code, you might like doing CAD in code. If you don't like writing code, you might never want to touch this. But for 2D things, it's plenty simple. Like with 3D things like this, I probably would not bother. I would use, you know, Fusion or something. But for two-dimensional things, it's rather convenient. So I'll show you what I mean. I'll whip open our Openscad, and we'll do something new. And I think I can make the text bigger. Whoops, that's totally the wrong place. There we are. Cool. So the way this works is you write little command things over here, and then you can see your result on the other side. In fact, actually, I have with me today another link. There you are. This one's again going to be in the links at the end, just like a little cheat sheet of some of the things, which is kind of useful. But we're going to be doing very, very, very simple things today. So, for example, our board. I think we're probably going to have it mostly be a square. Maybe we'll toss on some rounded corners, and it's going to need screw holes at some point. Or maybe not a square, maybe more of a rectangle. So to do that, you can go ahead and start with square. This little function here, you can see once you open like a bracket, it'll give you some help options. So today we'll do the second thing it's saying here, give it a width and a height. So the size of our board, and sometimes if you're designing this in real life, you'll need to go back and forth and see if these things fit on this size of board, and then maybe change your outline to make it bigger if they don't. You'll have to bounce between KiCad and whatever you're designing your outline in. But today, I know what size it needs to be. We're doing 16 millimeters by 32 millimeters, so a nice 1:2 aspect ratio there. And we can go ahead and take a look at what that looks like. To see what it looks like, you can press F5. Just kidding, put a semicolon on the end, then press F5. Or there's this little tiny button down here that says preview that'll do the same. Here, this acts more a bit like a CAD program. It's the view, and you can drag it around and look at it, zoom in and out kind of thing. What we probably would like, just because I think it would be convenient, is to have this centered in the middle of our thing though. So when you're drawing these square things you saw a second ago perhaps, it had this other option here. It almost looks like Python, a keyword argument, where you could write center equals true. So if we try that. Whoops. American spelling, of course. There we are. That centers the shape in the middle. Excellent. We've designed a rectangle. So that's honestly not too different from what we did in PCB new, except this, of course, we can specify an exact number of millimeters without having to count it ourselves. So that's kind of nice. But let's do something that we couldn't easily do in PCB new, which is add a rounded corners around it. So Openscad has this function called Minkowski, I think. Oops. So I'll put that on its own line. Minkowski. And basically what this wild function does is it takes whatever shapes you put in these curly braces, and it will run the second shapes around the first one, like the perimeter. So imagine you took a circle, a little cylinder, so in fact we'll draw a little, will I bother? Can I comment lines? Sure can. Okay, so yeah, I will. So circle, and is there a nice way to comment everything there? The answer is yes. Control D. So if we do a circle, this is easy enough. It tells us just pop in a radius. If we want a radius of 2, just put in 2. Render things. Oops. Render things. You can see actually that looks like a pretty awful circle. It looks very bumpy. The reason for that is because when you're designing lots of things like laser cutting profiles, which is what this program can be used for, or things like that, it approximates curves, and this is a very small circle, I guess. So it obviously looks like a hexagon. To fix that, there is this little setting that you can set. Special variables start with a $sign, then a $FN. That's like the number of refinements, I guess, around circles and things. So we plot that at 50, for example, and then render that much more round. And you can still see a little bit there. You can make it something obscene like 1000, but that slows down render times and things. Maybe we'll pop it at 100 for the time being. Keep it a bit in the middle. Just kind of interesting. But the idea, if you imagine taking this circle and moving its center point around the perimeter of a rectangle, so dragging that circle around this rectangle, then you could imagine that might add some rounded corners. It will also add 2 millimeters to every side, since that's the radius of our circle. So we'll need to decrease the size of this square a little. So we'll do -2 on both of these. So 14 and 30. And then we'll use this Minkowski function, and that is what's doing that dragging of a shape around the perimeter of another shape. And so we can go ahead and grab that up there first, and then add, oops, is that not properly indented? It was not. All right, and then circle 2, lovely. Pop that in, and voila, you've got some rounded corners. So of course, like, if you are the programmy sort, you can start to imagine how, because there are functions, there are for loops, you can import things. You can start to imagine how you could have some very like flexible CAD designs, but it's just another way of lots of ways to skin a cat, I guess. Although I don't necessarily advise skinning cats. It's probably not a good thing to recommend morally. But anyhow, there we are. That's lovely. This is a preview. That's what we get with F5. If we render the thing, because this is actually still a 2D shape, it will give us a 2D profile. So if I press F6, renders things, plays a nice little noise for us, and there's our second up button down there. If you like buttons more, there's the render one. So there's our nice profile for the outside of our PCB with rounded corners. Now what I can do is jump up to File and go over Export. Whole bunch of export options as STL. Well, I won't read off all of those. There are lots of options. The one relevant for us, because PCB New can use it, is this DXF format. So if we grab DXF, then we can pick a place to put that. So I need to go all the way into Downloads, University, Miscellaneous, Societies, Bionics, Bootcamp, PCB, Tutorial Vibes, and Bootcamp. Woo! Took me a while. All right, outline .dxf. That's what we want to put there. Beautiful. And now what we can do is add some screw holes to this. So we'll be putting 2 millimeter screw holes in it. So let's think about a way we might be able to do that. If we have this shape here, how will we programmatically create holes in it? Well, a way you can do that is with another function. It's the difference function. So difference just takes the first shape in its little block and then removes all of the other shapes from it. So if we put our rounded rectangle as our first shape here, indent that properly, and then we remove from it a circle that is, I think actually these are circles that are 2 millimeters in diameter. Let me double check with my notes. The answer is yes, sorry. Yeah, so these circles that we're gonna be putting, or the screw holes are 2 millimeter diameter. So you can see here if you use D equals, you can specify a diameter with circle. So we're gonna do D equals 2, and then leave that like that. And go ahead and see what it looks like. Don't forget your semicolon like me. Et voila, look at that, screw hole right in the middle of the board. That's probably not where we want it. So there is a way to move that. Just like with these difference in Minkowski things, you can transform the shape by applying some operations to it. So we can use something called translate, just moves something. And then you can give it an X, Y, and Z coordinate of the translation. And this is in the same units as before. So from the notes tutorial thing, we have, if we do moving it 7 millimeters on the X-axis and 15 on Y, put that in front of circle like that. Now you can see it's in the corner, so that's lovely. Now you can imagine if you want to put these in all 4 corners, you could do so many clever programming things. You could use a for loop, you could use mirroring operations, or, I mean, to be honest with you, another benefit of doing simple things in code like this is you have the magical function of copy and paste. There are fancier ways to do this, but this is a very niche program, and so we won't necessarily be spending all of today learning just how to use it. So here we can just think, well, all right, this one's up in that corner, and we just tack negatives onto that, and then negative onto both. And that'll put us in all 4 corners like that. Awesome, and I'll also make that look a little bit nicer alignment-wise. Not that it matters at all, but there we are. Cool. And this, if we render that, is going to give us the same outline, but this time with screw holes. So we can go up to our file, export, and then DXF, outline, but now we want outline, screws. And then go ahead and click save there. Lovely. Okay, that is all for today's brief tour of this bizarre Openscad program. But before we jump back, do people have any questions about Openscad? Openscad? I don't actually know how you say it. Thoughts, comments? Are people Openscad fans, or do you never want to see it again? Can I do everything that Fusion could do? Well, to be honest, I've not actually played with it a massive amount. I think Fusion, honestly, probably has some more capabilities. I think you could probably pull off more easily in Fusion, but technically, given that this is something you can program and add, like, imports and libraries to, you might be able to pull off some very fancy things. What this is good for is if there are some shapes in the world, and not all shapes, but there are some shapes in the world that are much easier to mathematically define than to actually make. So, for example, if you wanted to make like something that spiraled, like a Fibonacci spiral, you could try in Fusion to use a spiral tool and try and convince it to follow like the Fibonacci series or something. But here you could just compute the Fibonacci series, because it's a programming language, and then just directly draw it. So I think they're good for different things. If you want to do things that are very like mathematically defined, this is an excellent way to do it. Otherwise, Fusion realistically probably has some more capabilities. But if it does come to two-dimensional things, this can probably do everything that Fusion can do. Can you export it? Yes, you would be able to export it under up here the export as STL or even 3MF. I think both of those are big or decently popular 3D formats. It won't be like a first-class citizen in Fusion. You won't be able to like directly edit the spiral or whatever, but it would be like downloading something from a 3D printing website and editing it there. So you would be able to bring it into other programs for sure, yeah. But, awesome. Yeah, a bit of an interesting little detour, this Openscad thing, but I think it's kind of neat, to be honest. So I figured I would shout it out since this original tutorial did, and it's a really nice way for me to make two-dimensional things. Like, for example, I guess, now that I've destroyed it. Well, actually, I think I saved it. So if I go to Openscad board outline here, did I go somewhere? Here it is. Yeah, here, the other PCB that I designed for Avalon, the rover thing, was a weird PCB where I wanted to have two layers to it almost. This was a light ring up here, so that had a bunch of LEDs on it. A camera would go through this middle hole, and then most of the electronics would be on this back motherboard place. So this I designed here at Openscad as well. It's very cute if you just want the difference. I just did two different diameter circles, and then that was done and fine. And here you can also see I used a for loop as like a pattern to put these things around. I used a rotate 90 degrees in 0 through 1, so that's rotating all these holes around. So I only need one circle here, and if I change like the diameter of this to like, I don't know, something big, 7, and hit re-render, you can see now they're very big holes and they all get duplicated around. So it's a lot like parametric modeling in Fusion, but programmatically, so. All right, that's all for the Openscad detour. Don't need to save that. Excellent. Oh, yeah, that's a good question. I think the answer to that question is it looks a little bit like a language like C or C++, I agree. I think, off the top of my head, though, it's its own programming language. It's a very simple programming language. It has like list comprehension-y features, almost like Python, sorta, but it's very, very, very specialized to just do this. I don't think it's like a general-purpose language. But you can probably find out a bunch from that cheat sheet. That cheat sheet has a nice bit of a reference there. But yeah, it's its own language, I think, which is very neat. Cool. Good questions. Nice. Now we have to import it into PCB-Do. We get back to making PCBs after that fun little detour. So to do that, we can jump up into File, and Import is one of our options here. Hello, there we are. Import, and then import graphics should be the second option down there. So if you import these graphics, you can go and pick them in your file browser. So I created a root clamp instead of Bootcamp when I was testing this morning to give them different names. I know, I'm incredibly good at naming things. We'll bring in our outline first. So here, you can either do interactive placement with a mouse, which is one thing, and that's fine, but it might be a bit difficult for us to perfectly line up both of the outlines. So what I'm going to do instead is just say, put this at x50, y100 units and millimeters. So that'll just put it in a fixed place on the board. This is important down here to pick the layer. So we want edge cuts. Remember, edge cuts is the actual part of our PCB that's going to be cut out. We want this to be our outline. So our outline is actually defining the edge of the board. So that's fine. It is hard to read. Very challenging. Yeah, I tried a couple of things this morning to get it to be a bit bigger, but it was difficult. So I'm going to have to try and read things, I think, verbally, and the recording should catch things if you miss any, but I agree, it's definitely not ideal. I'll have to figure out this, because other programs, it's very easy to make them bigger or smaller. I've had trouble doing the same, unfortunately, with PCB New and KiCad. But everything here has been left at defaults. Up here, I went and picked the DXF file that we just generated from Openscad. It's saying at X and Y, so this is a fixed placement position, and I'm picking edge.cuts layer as the edge of the PCB. I'll go ahead and press OK there. So now you can see, over here, we have our shape. Been very nicely imported, beautiful curves, everything we were looking for. Now what we'll do while we're at it is we'll also go and import our second layer. So import graphics, and now we're going to go browse outline screws. So this is the one with the screw holes in it. Keep the exact same placement position, but now change the layer to be eco1.user. These user layers don't actually get used by the PCB manufacturer, really. They're just there for you to look at as the designer, and they can be helpful guides. So the reason we're putting our screw holes here is because the screw holes we're making are actually going to be a footprint that we put on the board at the very end of the process. And these are just kind of serving as an alignment thing. We're not actually going to cut these out of the board directly, because there's a nice footprint that does that, but with like some metal plating and things like you usually see on screw holes on PCB boards. Again, rest of the things we're leaving at default, and we'll go ahead and hit OK. Lovely. So now you can see, here's our board. You can even see the different colors. The yellow outline is the cuts layer. As you can see over here, edge cuts is a yellow color. And the green one here is the Eco1 user. So that's just our reference layer. Awesome. Now, what we need to do is actually put all of these components onto this board. So in PCB New, like in the schema program, which we use to edit schematics, pressing the M key. M is the shortcut for moving things. R is the shortcut for rotating things. Shift R will rotate things in the opposite direction. Just some basic things there. Cool. Now, here's where you need to think about a lot of physical considerations. The first of which being, what parts of our board need to be in a particular place? So for us, remember, this is going to be a little development board that we can put into a breadboard and then connect other things to it, write little programs on it. A bit like a miniature Arduino, except I guess it'd be like an Arduino Nano if you've ever seen one of those that has spiky boys coming out of the bottom. Or it might be a Mini, sorry, not a Nano. Arduino, no, it's definitely Nano. I'm thinking of Raspberry Pi Mini. It's going to look something like one of these, where I wish you would show me actual pictures, please. There we are. Nice and hard to see, I am sure, but hello, where is the view image button? There is not a view image button? Well, very exciting. Point is, there you are. That's what it'll look like. Something along those lines. where it has things that stick out of the bottom that you can jam into a breadboard, and this little programming header on top of it. So what we need to do then is make sure that these are correctly spaced so that they fit into a breadboard. This is something you don't think about often, but if you accidentally buy something that fits poorly into a breadboard, it makes you incredibly angry. As I've discovered, some of the ESP32s I have are slightly too wide, so if you put it onto a standard breadboard, you can only access 1/2 of the pins coming off of it. Infuriating. So you can imagine how frustrating it would be if it didn't fit into a breadboard at all. Luckily, breadboards have a standard spacing, so if I search breadboard pitch is the word for like the spacing between holes in electronics. Well, point is, we don't need to read the whole Wikipedia article. It's gone ahead and showed us the information that we're looking for here, which is the spacing between the holes. The pitch is typically 0.1 inches. And as frustrating as that is, it's correct. So breadboards and so many things in electronics are in absolutely revolting imperial units like inches, and a new one I get to introduce to you today called a mil, and it's not a millimeter, but a mil is 1/1000th of an inch. Anyways, the pitch, the spacing between the holes, 0.1 inches, so that's going to be 100 mils. That's how far apart our pins coming off of our PCB will need to be. So if we hop over here then, these, remember, are our GPIO things. So these are the things that we are going to solder those pins into. Those need to be spaced correctly. So if we go up to our grid, what we can do here is pick the correct pitch, which is going to be way up at the very top. 100 mils, it says over here on this side, and it says 2.54 millimeters on the other, because that's just the conversion between millimeters and, between inches and centimeters there, basically. So we go ahead and do that. Now you see if we grab and move one of these, it snaps in much bigger increments, and each one of these increments is basically one row on a breadboard. So what we can do is pop it down here, and think like, that's an alright place for one of them. I've determined that's a bit high. So we can move that down one. Well, it doesn't really matter. We can move the board outline after in a second. And then this here, that's obviously the same height. And then we can just shift it over. I am going to move these up one, actually. And do something like that. Now you can see, obviously, this is far from centered in our board. And if I go over, it's outside of the board. Bit of a disaster, right? Luckily, what we can do is our boards don't need to actually stay in the same place. The only part that's important is that this spacing is snapped to this grid. So GPIOs are in the correct place now because we've had that grid setting. Now what we can do is take our grid setting down, something much smaller. I'll do 1/10 of a millimeter, so that's basically almost just kind of off in terms of the snapping. It moves basically wherever you put your mouse. And what we can do is click and drag with your left click to select everything here. And there's a neat little feature. If you right click, there's this little option here that says select. And under select, you have something called filter selection. And if you go to filter selection, you get some tick boxes. So this one says, would you like to include footprints in your selection? Would you like to include tracks? Would you like to include vias? Would you like to include text items? Things like that. These important ones here are include drawings. Our holes here for the screws are drawing holes. And the board outline layer, which of course is our edge cuts hole, so that's the outside of our PCB. Those ones are actually the only ones we want to move. So we can uncheck everything, but keep, that one won't let me uncheck it, but that's fine. Because we don't have any locked footprints, is what that one says. But here we're just moving drawings and the board outline layer. So go ahead and click OK. You see now our GPIs are unselected. Our board is still selected. It's a slight color difference. And if I press the M key, I can now move it with my mouse. So here we're just going to pick something that looks actually somewhat centered. And I might push it slightly lower on the board as well. All of this is, there's a lot of eyeballing and guesswork in this program, which kind of hurts me on a deep spiritual level, but it's important to realize my grid currently is working at 1/10 of a millimeter steps. So if it's off by a couple of grid snaps here, that's so unnoticeably small it won't cause you any issues. This whole board, it's important to recall, is very, very, very tiny. I guess it's only, what, 1, 2, 3, 4, 5 breadboard holes across, probably. Something like that. So it's very, very tiny design overall in terms of like this page. I think that's like almost an A4 size page of paper there. It might be hard to see that dim red outline, but I'm kind of circling it with my mouse. So small board, so don't worry too much about the tiny and, well, not precision-y bits. Something we can do to make this look a bit less chaotic, because you can see we have lots of like overlapping text here, is we can toggle off one of these layers, and it's down called ffab. So f.fab, that's a layer that just holds a bunch of information. It's like our annotations that we made in our schematic, so it tells us this is the GPIO-B, GPIO-A, but we don't actually need that. That won't actually show up on the final board ever. So instead we can turn that off. A bit nicer to look at, a bit clearer to move things around in. Cool. So real quickly, I will check in with people. How are people doing? I know things are tricky to read. Have I lost anyone anywhere? How are people feeling so far about this? I guess just give me a thumbs up or thumbs down somewhere. Should I use a Discord poll, or do people just want to put it in the chat? Everyone seems to miss the polls. They must. Happy so far. Okay, okay. Awesome. Okay. Well, you beat me to figuring out how Discord's poll feature worked again for like the 5th week in a row. So, excellent. Good to know that people are doing well so far. In that case, what we can do is continue to align the rest of things kind of roughly. We don't need to be too precise about moving things around right now because, as a bit of a spoiler alert here, things are going to move around a lot once we start routing traces, because we're going to need to make room to connect things electrically. But for now, for example, we can plop our microprocessor in the middle of those two lines. That seems logical. We'll put our programming header maybe at the bottom here. So that's not what I wanted to do. So I can go ahead and hover over this and bring that down here. So now you might notice, or might have noticed already, that sitting around are some white lines. And these white lines seem to be connecting different pins to other things. They look like a disaster right now, because they're overlapping, very messy. But that's called the rat's nest. So what the rat's nest is... Oh, wow, okay. I'm going to need to move things up, I think, because I don't quite have room for this. It'll be fine if I move them together, because the spacing will be fine. So, there we are. I think it should be fine if I select that and, well, select this GPIO, that, and this, and then move all of these upwards. Is there a way to snap it to just be vertical or horizontal? Not exactly. Our grid is very small, so I can't quite tell. So I'm going to real quickly turn up the grid size. So changing the grid size is probably your most friendly method of precision in this program. So I've changed it up here to be 1 millimeter now. So now everything's going to move in 1 millimeter increments. So I'll select all 3 of these again. And then I'll click M to move them and pop them up 1 millimeter probably. And I think that's all I wanted, actually. So that was 1 millimeter of distance. So maybe that puts the scale in perspective. Oops. That big movement there. These big jumps, those are single millimeters that we're moving things. Cool. I'm going to drop back down to 1/10 of a millimeter just so I can kind of place things where I'd like. And I'm going to grab this bottom thing here, kind of center that between these two reference points, which are our GPIO lines. Move it up there. Nice. That looks fine there. Yeah, but the rat's nest, you want to try and untangle this as much as possible. Whenever you have a direct line, for example, like this SW clock has a pretty direct line to the thing it needs to connect to there. That's going to be really easy to route. When you have things here, when you have crossing lines, like these GPIO lines, so you see 4s having to cross both 1, 2, and 3, and 3 is across the whole board over to the other side, that is going to be a disaster and a bit of a mess. So we're going to address that in a moment. Before we do that, though, we'll just plop the rest of these things onto the board. So yeah, let's grab our battery connector next, I guess. Oh, whoops, didn't mean to do that. Battery connector, grab that with M, rotate it with R. I'm going to plop that there. Yeah, that's okay. Switch, we're going to need to put that up on the top of the board. Exciting. Okay, yeah, so you can overlap, by the way, the text stuff. We'll move that around later. This blue or tealish color, that's the silk screen. So that actually will be printed on your final PCB, usually in white, although you can have it in different colors. But don't worry if those are overlapping now. You can always move those around later. Go ahead and do something like this. That looks somewhat centered between those two screw holes, I guess. And somewhat centered is kind of all we're going for at the immediate moment. We'll be more precise later. This is our power regulator boy. Linear regulator, sorry, that's the actual term for it. Not a power regulatory boy. So there's that. We'll grab our capacitor here. Oh, hey, this is actually a very important part. Recall, decoupling capacitors need to be as close as possible to the thing that they're insulating from electrical noise. So I happen to remember capacitor 1 is our decoupling capacitor. If you don't remember that off the top of your head, you can always just go and check in the schematic program and then go over here. This is our decoupling capacitor, and that is C1. That needs to be as physically close as possible. Well, as physically close as practically possible to the pin that it connects to. So, for example, this 3.3 pin, as well as ground. Ground, we're not actually going to wire up directly, and you'll see why a little bit later. We're going to use something called a fill layer or a copper pour. But we do want to get this 3.3 thing as close to this 3.3 here as we can. So we can't put it obviously inside of this microchip or on top of our GPIO lines, but we can certainly move it pretty close. So I'll move it there for now, I reckon. And I'll move that over there. Hovering things and then pressing M will move them, and that works for anything on the screen, usually, even this individual little labels. And you can tell those are tied with this little blue line. I just used my finger to point at something. Sorry, that's not terribly helpful. I'm moving it in the direction of the blue line here. That blue line, that's what tells you what part the silkscreen element belongs to. So this U1 is labeling this first microcontroller here. Also happens to be our only microcontroller, of course. Cool. So those will have to be connected. Here's a second capacitor. These ones are just the power regulation capacitors, so those ones are much less finicky, I guess. So this one, we'll probably need to move that around a bit. We'll shuffle things up there a little bit, maybe. Do something like that, I guess. We'll see if that gives us any issues. Lots of this is just moving stuff around and then trying it and then moving again and then trying again. So don't worry if this takes a little while. Depending on the complexity of the board, it can be brutally difficult sometimes. What does that say? Net D1 pad. Oh, you want to be connected to the diode. You have the diode resistor. So here's our LED. So this we can rotate around and put somewhere up here. I'm going to overlap these silkscreen things for a minute. Is that bad? You know, I'm actually going to grab this. I'm going to tend to the silkscreen a little bit as we go, just to keep it easier for us. I'm going to move the battery connector farther over. And then I'm going to move that there. Diode resistor is here. You can see in the rat's nest, this LED pin, remember that's going to be connected to our microcontroller. So actually, if we rotate this around to have the LED pad closer, you can see that untangles our rat nest a little, because here we have it going in that side, coming out this side, but when it was rotated around, you can see they're kind of crossing. So this line is going to the farther away one, this one's going through that pad to that one. So you're trying to untangle, essentially, all of these white lines the best you can at the beginning. That's the idea. So I'll rotate that around to be untangled that way. And that's cool. I'll put that in line with the battery connector here, but a bit over, because in between the battery connector and that, oh, whoopsie, didn't mean to grab that. We'll put this resistor here. So notice that this is also connected to that LED thing. So if we spin this around this way, and again, I'm pressing R to rotate things, now you can see our rat's nest just goes directly over there. In fact, just to keep it clean so that I don't have to think about it right now, I'm going to hide the silk screen. So I think you can do that with it. Is it the paste layer? No, I need to find the right color one. Oh, there it is. It's called f.silks for silk screen. That's front silk screen. So I can turn off the front silk screen for now. I'll do that just to make it a bit easier to look at. We'll turn that back on later. Just got to make sure the white boxes don't overlap. Those are called courtyards, I believe. That's just like the personal space of each little component that you probably shouldn't try and mess up, or you might have trouble soldering things, is the general idea. Ah, see, there's a downside to that. I don't know what these components are anymore. Okay, welcome back, silk screen. This one's a resistor. Cool. Where does that go? That needs to go to the reset button and 3.3 volt power. Well, reset's up there. So if I spin it this way, untangles that rat's nest pretty easily. Lovely. And you, my friend, where do you belong? You belong between ground and 3.3 volts. I'm going to switch you with capacitor 2, I think, because that needs to be connected to the battery power and to ground. And so actually what I'll do is spin this way. And if this seems like I'm making this up as I'm going, that is because I am. I've done this morning, so I've made this PCB board, strictly speaking, only a couple of hours ago. But there are so many different ways to do it that you can change your approach, and that's totally fine. So there we are. Okay. Things are on the board. It looks hideous and disgusting, but they are there. So next thing we need to do is actually start electrically connecting things. So yeah, let's get started with some of the simple ones. First of all, make sure that you selected your front copper layer. So it's f.cu. You can do that over here, this front copper layer, or you can also do that up here. This is another layer selection dialog. So we select that front copper, scroll on in, new keyboard shortcut for you. You can press the X key. If you press X on your keyboard, that puts you in the trace drawing mode. You can also click over here on the sidebar. It's this thing that looks like a little squiggly line for routing things. Then you just got to connect the rat's nest. So I can click on, for example, this thing, one that we said was easy earlier. So this SW clock, I was going to do that, but then I realized this wasn't centered. That's also not centered. Literally 1/10 of a millimeter, I will not notice, so I will leave it alone. So if you press X to lay some traces, I can click on SW clock here, and you see it dims everything but highlights the thing I need to connect it to, and even gives me a nice little yellow thing. KiCad, is usually pretty good at figuring out how you want to connect things. So you can kind of just move your mouse to go and click on something, and it will make it nice 45-degree angles, make sure it has enough space. You can even wrap it around other things, and it will figure it out. But obviously, as is probably common sense, the shorter the connection, the better. So at least in this, there are some special exceptions to that, where, for example, remember we often idealize the world a lot in electronics and say, oh, these wires, they just perfectly conduct electricity, right? In reality, they have some capacitance, they have some inductance, and this can change the properties of things. So if you have high speed signals, meaning that like they're switching between 0 volts and whatever your high voltage is really, really quickly, going between ground and your high voltage, alternating like signal wires or some sort of sensors doing this communication that's digital, those you'll have to think about a little bit more sometimes in terms of noise, how you route those. Maybe if one trace is longer than the other because it has to be, you might artificially make the other one longer so they're the same length, so you don't get any weird effects. I think that's actually what this is. Show or hide microwave toolbar. Well, I don't actually need to do that right now, but that's some stuff for like if you're doing if you're designing things to be resistant to interference, electrical interference. Cool. Okay, that was enough blabbering. Click on the end thing, and there you are. It's drawn a connection between the two. Those are electrically connected. Fantastic. Let's do the same for some other easy ones, like just reset one, go around there. Excellent, nice and pretty. SWDIO, simple, straight connection, no problem at all. Ground, we're not going to pay attention to ground yet. Again, we're going to leave that be 3.3 volts. We can connect that. We can take these traces inside of the white boxes because the traces are totally flat because they are just, I'm going to try and go a bit farther over here. Is that going to be fine? Well, it's a bit squirrely. I don't know how I got it to not do that wiggle earlier. Oh, it must have just been because of where I had my thing. Oh well. Literally doesn't matter. So, the point of that, connecting that up there, you can route things underneath the chip. It'll make sure it doesn't interfere with other copper. Basically, you just can't connect your copper wires to other copper wires. But since they are totally flat on the surface of the PCB, you can put the physical chip on top of it here. It'll probably be in like a plastic package, and that plastic won't have any problem touching these copper lines down here. In fact, these will be covered by what's called a solder mask anyways. So these are fine to route into the white boxes, but you can't clash white boxes with each other because those are physical parts. These are printed bits onto the board. So that was a long way of saying that's a fine way to connect that. This 3.3 power we can take up here to the decoupling capacitor. That's a relatively short distance, about as short as we can get it on this board without moving GPIO out of where we want it, so I think that's fine. LEDs we might want to connect. We'll have to think about how we want to connect that in a minute, I think. In fact, I might connect that before the other one. Well, okay. We'll deal with the bigger problem first, actually, and then we'll round off the rest of it. The big problem, like I kind of hinted at earlier, was how crossed the rat's nest for these GPIO things are. This is because sometimes the way things should be is not the way things are. So, for example, if you're counting, well, if you look at these pin numbers here, they make sense physically. You have 1, 2, 3, 4, 5, 6, etc. 7 and then 8. So you're going like counterclockwise around naming the pins. Fine, sensical. If you go and look in our schematic, however, remember here we nicely lined it up so it's 1, 2, 3, 4, 5, 6, 7, 8. So that's very nicely numbered. These smaller numbers inside are the physical pin numbers. So here you can see pin 1, physical pin 1, is connected to GPIO 4, but then the next physical pin over here is connected to GPIO 1. So that's where we get like this weird cross of there's the second physical pin being connected to 1, but the first physical pin being all the way connected to GPIO 4. So that's a disaster. What we can do is just take a look at this, come up with the simplest possible mapping. We have 1, 2, 3, 4, 5 lines here to connect up to that to GPIOs, but there's only 4 things on the side, so actually what we can do is change one of these to be our LED, because remember our LED is just a GPIO output. And then over here we'll have 1, 2, 3, 4 GPIOs, so those are actually already perfect to go there. So let's write up a little mapping. Then what we can do is change the schematic, and then we can reload it into our PCB program. So I'm gonna whip out world's fanciest tool, essentially Notepad. Going to try and make this zoomed in bigger. Don't actually know if I'm going to be able to do that. Now that's going to be exciting if I can't do that. I'll have to do that. Alright, now we're whipping out the really ridiculously big guns. Cool. Emacs, hello. This is a wild, like, document editing text thing. That was really vague. It's an IDE almost for programming, but also does excellent like note-taking stuff, so I use it to take university notes. So here we are. Welcome. We'll create a temporary file in our documents folder, I guess. In fact, I'll name it .org so we get some special features. Okay, and then this I can make bigger. I think. There we are. Yes, okay. Wow, that was a bit of an adventure. Point is, at least you should be able to see the things I type now. Cool. First of all, I want this first physical pin to go to the LED. So if I do that, I want to do 1. I would like that to go to the LED. Or I guess I should probably use their label. So D1 is the diode 1 label. It doesn't actually matter. LED's fine. For 2, here, where do we want that one to go? That one's actually fine as is, I think, because that's going to go to this first GPIO up on top. So I'm going to map that to GPIO 1. I'm going to do GPIO 1. Just kidding, we're going to do G1. For the next one, 3, that's also actually going to a fine place. So we're going to do 3, still going to GPIO 2. For 4, where's that one going to go? 4th physical pin should go down to GPIO 3, I think. So that keeps our nice things all on the same side. And then finally, of course, 5, also on the left side, down here. That's going to go to GPIO 4. So there we are, nice and easy. So that one actually isn't too bad. You're just kind of shifting things by 1. Where it starts to get stupid is this other side. On the other side, now remember, despite there being a 1, 2, 3, and 4 here, I'm going to go off the GPIO 5, 6, and 7, and 8. So starting at 6 then for GPIO, well, no, what am I talking about? Double checking, yeah, these are corresponding to those physical pin numbers, fine. Yes, the reason this gets weird, sorry, is because the mapping almost switches directions. For example, the first GPIO pin up here is now not 6, it's 14, because we're numbering around counterclockwise. So 14, we want to point to GPIO 5. So that's a GPIO 5. And then for GPIO 6, our next GPIO thing is down here. That's our LED one, so that's 13. So 13 can go to 6. And also, sorry for the tediousness of this process. This is this way because, well, chips are weird. I'll show you in the data sheet in a second that because they make one electrical chip but in different physical forms, sometimes the pins just make no sense. But writing all of this down now just saves us the effort of having to like go back and forth between this program and the schematic program. So that, for example, should go to GPIO 7. And then 9 over here should go to GPIO 8. Cool. In hindsight, if you are me, I would have done these ones first, since these ones go in an order, and then said which point on the this thing they point to. So I would have switched the left and right sides of these arrows in hindsight, but hey, you live and you learn. Cool. Okay, that's out of the way. Let's actually update the schematic, see if that resolves our nasty rat's nest problem. So just before we go, remember the issue is like this GPIO here, actually if I click on it you can see, needs to cross the whole board to get over there. Now KiCad will decide, oh okay, I can route it up around that. But once you start getting traces that look a bit like that, that's when you know you might want to start looking for other solutions. Because it's very much a simpler is better kind of thing. So if you're doing crazy stuff like that, maybe rethink the layout. So let's jump then, save that, to Schematic. Hello again, Schematic. I'm going to make you half of the page. I'm going to make you half of the page. Make you much more of the page. Okay, so lovely. I'm going to keep all of these GPIOs the exact same. I don't want to mess up that ordering, remember. But what we're going to do is shuffle things around on the microcontroller, these little labels here. So we're going to start at pin 1, which is here physically, because of course it is, it's in a random place. And we want to connect the LED to that. So I'm going to grab our LED. Remember M to move things around. So M to grab the LED and put it there. Physical pin 2, which is all the way over on this side now, should be pointing to GPIO 1. It is. That's awesome. Pin 3 pointing to GPIO 2. It is. That's awesome. Now we get to physical pin 4, which is down here. We want that to point to GPIO pin, or GPIO 3. So grab GPIO 3, move that down to there, to 4. Then we want to grab physical pin 5. That's going to be GPIO 4. Hopefully now you can see why I spent the time to write this down in a text document instead of just trying to shuffle them on my own, is because it's a disgusting amount of shuffling. Pin 6, physical pin 6. Don't care about that at all. In fact, pin 14, though. Physically is there. We want that one to be GPIO 5. Pin 13, GPIO 6. Pin 10 should be 7, and 9 should be 8. So there we are. So after that revolting process, go ahead and save the schematic, I guess. And once the schematic is saved, we just jump over here, and here's the real magical step. This is why I'm happy that KiCad makes these programs play together so nicely. Just go up here to your Tools again, and inside of Tools, you can do Update PCB from Schematic. So remember, this is the very first thing that we did to load in all of our stuff. So Update PCB from Schematic, keep it at your default option, smash Update PCB, and et voila, it keeps the positions of our footprints because we haven't added or deleted any footprints, but it now reconfigures the rat's nest to show us the new connections that need to be made. So here we are. Look at that. None of these lines are crossing anymore. Very nicely lining up with all these GPIO things, and the LED also has now a clear path up there. So excellent, we've sorted that rat's nest problem there. Stuff up here might still be a bit chaotic, but we'll come back to that in a second. First of all, time for the satisfying part. Once the rat's nest is sorted, it's very nice to just press X on your keyboard to start routing things. Whoops. And then click on that pad, and just click on the ones that get highlighted. And the tracing it does to make kind of nice and pretty looking on its own, which is excellent. Just like that. Clickety-clack. And boom, most of the things on our board are now connected with one easy trick. Awesome. Cool, so we have now a couple things left to route. For example, this connection here. Easy. That's just a straight line. Ground, remember, we're ignoring for a while. We'll connect power, though. Is that fine? I'm trying to look ahead a little bit here and think about how I'm going to get this battery all the way over there. And I think that will be okay. Yeah, that'll be totally fine. So I'm going to click there, route the battery. First route it to this. You can see it's automatically routed through the middle of these, which it can do. If I zoom in enough, you might be able to see it. Not really. It keeps the line very thin. If you're lucky today, and I'll answer that question in just a second. Excellent question there, Philip. This little tiny red outline, I have no idea if you can actually properly see that. That's the exclusion zone for traces. So traces can't be inside of that because otherwise they'll get too close to this copper. They might short it out. But here you can see there's a nice big gap still between the pads, so we can write or run traces straight through the middle of it, which is really good. To answer the question that Philip has asked, how does the ground work again? Hopefully you'll be able to see in just a second basically what we'll be doing after we've drawn all these little connecting lines. And you could, by the way, do the exact same thing for ground. That's fine. You could connect all the ground things up the exact same way we're doing now, and it would work. But there's an easier way, easier as in faster, and sometimes, depending on what you're doing, better for electrical connectivity as well. And that's just to take, after all of these traces are drawn, dump copper everywhere on the rest of the board, and that's the ground. So anything touching that giant, continuous filled area of copper is going to be connected to ground. And so I can go in and connect all these things for us. And there's a nice tool for doing that. And it's not wasteful either, because the way that they make PCBs, at least if my memory serves correctly from when I watched a How It's Made, dozens of years ago, is you start with the copper on the board, and then you acid remove copper where you don't want copper. So to fill your entire board with copper is not really wasteful because that's how it starts. So don't worry about fills being, I guess, wasteful. Cool. We'll wrap our rest of our things. Oh, look at Brooks. You've made it very easy for yourself now. So I can click battery there, connect these battery connectors that are right next to each other. 3.3 volts. Hey, what are you doing there? That's a bit of a weird way to go around. Go up there. There we are. 3.3 volts, 3.3 volts, 3.3 volts. Connected to our reset line. Awesome. All we have left then is... we need to get the reset button somehow way down to the bottom there. Are you intruding on the 2 ground? Where do you mean? Oh, here you mean. This thing. Is this the pad you mean? Here? Yes, I don't think we are. By default, KiCad will not let you. It makes sure that things are at least some minimum distance, and you can configure that distance depending on your PCB thing. But like, it won't physically let me get closer than allowed, I guess, if that makes sense. But you can see here, it'll route straight through that other ground pad up on top because it knows they're electrically connected. But here, yeah, it's very, 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 very close, but don't worry, KiCad won't let you make that mistake, even if you try, which is good to know, because I need all the help I can get. Awesome. I have made... I'm glad I'm not the only one. I made the executive decision, I think, to spin this switch around. I would quite like to have the reset buttons closer to the bottom, since I need to connect it way down to this somehow. So I'm going to actually click Escape to get out of my trace drawing thing. Hover over this trace here, press Delete, the Delete key on my keyboard, that gets rid of that. And then hover over this, smash R a couple of times to rotate us around, and then move it again to be somewhat centered. And I know it looks like we're crossing lines there, not uncrossing them, but luckily the ones that are getting crossed are the ground lines. And to beat the dead horse further, there's a separate way that we'll be doing those in a second. Cool, that is as close as I care to be, I think, in terms of centering that. So now you can see this one last big unconnected rat's nest line that isn't ground is this reset one that wants it to go all the way down here. If I try and route that with X and then click on it, you can see it's a bit challenging to get in there. That's a bit of a weird path to take. That's technically fine, because again, it won't let you do anything wrong that's like not possible to manufacture, but it might be a bit cleaner if instead of going through all of these pads, we just went around the outside and then connected to this much bigger pad there, like that. And so that, again, has kept everything the proper distance over here, and connected everything up. Cool, I think that is everything except ground connected, so it's time then to play with ground fills. So I'll go ahead and save that. Real quickly, I will check in. How are people doing? Any questions, confusions, comments so far? I'll give everyone a second to yell at me. Excellent. Well, nobody's yelling at me, so either people are typing questions frantically. Yells fiercely. Wonderful. Definitely a relatable feeling when working with PCBs. Okay, cool. Good to hear that you were doing well. Hopefully the same for Maria. And I guess it's ground fill time. If you do have any questions that pop up, just smack them in the chat. So, now, to get on to ground filling. This is a really cool technique. You can even do it with power connectors. So I've designed boards before, and I've also helped now kind of design a board for Bionics, but it was mostly not me. It was mostly Shunsuke on the ARM team, I believe. He's built a lovely PCB for reading EMG sensors, his own custom circuit, which is really cool. So he has done a ground and a power fill, because remember, PCBs are at least two-sided usually. So you can make the back of your board a big plate of copper that is, say, your positive voltage, so our 3.3 voltage here or something, and then you could make the other side of your board the ground plane, so then you don't have to connect any power things manually, which is really nice. But today we won't bother with that. Instead, we'll just be doing a ground plane on one side. So it's going to be an entirely one-sided board today, which is, I guess, easy. Cool. So, ground fill. If you go over to Add Filled Zones, which is this little thing over here, it is 2 below the little squiggly line for drawing traces, and click on Add Filled Zones. I don't actually know if that one has a keyboard shortcut, but of course it does. The keyboard shortcut for that appears to be Control-Shift-Z. So let's do that. We love Control keyboard shortcut. So Control-Shift-Z has put us into this fill tool. See if I switch off of it, Control-Shift-Z brings us back to the fill tool. And then basically all we need to do is click somewhere outside of the board. And then here there's a whole bunch of settings. These settings by default aren't actually the most helpful in the world. So we'll have to tweak them a little bit as we go along. But first thing is you pick which net, which are like which pins you want to connect in this big fill. So ours is the ground, so we're going to click on the ground thing here, G and D. Here's some clearance stuff. I'm going to leave this at default for the moment, but we're going to have to come back to that. And then I'm going to press OK. So here, am I going to be a perfectionist about this? Of course I am, because I'm terrible. Okay, so I'm going to go up to my grid and click back on 1 millimeter, so we have a bit more of a coarse grid, so I can draw an easier rectangle. Then there, and go around. It's just important that the entire board is inside of this square. It technically doesn't, or rectangle. I keep saying square when I mean rectangle. It doesn't actually matter how big it is, though, so that'll do. Okay, there you are. That looks hideous. And in addition to looking hideous, it's only partially solved our problem. Well, okay, actually, there's a couple of issues here. I just am being dumb for one of them. I forgot to make a connection. So if I click X to draw a connection between the reset line and that reset line there, you can see, whoa, that's going straight to the middle of the ground plane. That's not allowed. That's just because the ground plane hasn't been updated. You have to update it manually. Usually, KiCad will let you know when it's out of date and help you. If you ever need to refill it manually, press the B key on your keyboard. So now you can see it's made a nice little cutout for that trace to run through without shorting anything. But you can also see lots of these connections, they stay very far away from things, and because of that, they can't flow into certain places. So like this little island of ground here is unconnected to the rest, so this ground pin is still not connected. So this won't work as a circuit. But luckily, what we can do is decrease some of the tolerances to get them a bit closer. It looks a bit Iron Man-ish. I agree. I think PCBs look super cool when you design them. Especially it's like this weird dark color background. Once you get two-sided PCBs, they're different colors on both sides. I agree. Very neat. And you know what? Oh, well, ignore everything I was about to say. I was about to say something like, it's even the right colors, too. A reddish and a greenish color for the other copper. But then I was thinking, wait a minute. Red and green are the colors of copper when copper oxidizes. Copper's not iron. Iron's in the name. Anyways, very tangential that. Point is, let's fix this filling problem. To do that, what we can do is check how small we can make these tolerances. Now, we aren't making this board by hand. There are technically ways to make your own PCBs, but they are high effort. You can get them pretty cheap, though, from a bunch of different manufacturers, and one that I think we've ordered PCBs from before. I know that the Avalon Rover people have ordered PCBs from them. It's called JLC PCB. So I will go ahead and smack a link that I have so conveniently hidden away. There we are. Welcome. Nice and big. So JLC PCB, great place to get some cheap PCB stuff from. And most PCB, well, all PCB manufacturers somewhere need to have something that tells you their capabilities. So here's what they can pull off. I sold you. So different specifications here. So this is a bunch of information about the physical board that they can make. So you have to design something within these parameters, otherwise they cannot physically manufacture it. So I'll send that away. What we're interested in is minimum trace width and spacing, actually. So here you can see, stop it, chatbot, I don't want to hear from you. Goodbye. Looks like a very friendly chatbot, though. Patterns is just, I guess, where they show things physically. Minimum spacing they're explaining, that's the room between two connections. And minimum trace width is the width of the connection itself. So if we want to push the minimum, we need to first look then, over here, at our copper weight and how many layers of a PCB we're doing. And these are things that you do when you buy it. Generally speaking, things with internal layers or more layers, like this 4 to 6 layers, or heavier copper, which means like the copper layer is actually physically thicker, those are more expensive. So for something as simple as what we're doing, we'll just go with the cheapest option probably, which is 1 ounce of a copper fill, just 1 to 2 layers. So for following 1 ounce, 1 to 2 layers, both our minimum trace width and our minimum spacing are 5 mil. Remember, mil is the disgusting imperial unit that is a thousandth of an inch. So they've also given us millimeters over here, which is convenient because those are the ones we can actually use. So I'll go ahead and copy that. And then what we can go ahead and do is for our copper trace, just like in the schematic editor actually, if you hover over something and you press E for edit, that will pop open a little edit thing. So you can see it's asking, oh, would you like to do these lines or the fill? In fact, both of those are incorrect. Maybe if I try here, yeah, there we are. So just go around on your fill somewhere, pressing E until it eventually gets you the right dialog. Then here, what we can do is take the minimum width there, and in fact we can probably do the same with clearance as well, I believe. Yeah, so clearance, we can paste in our new value, so our smaller 0.127. It was by default 0.508, so nearly half a millimeter by default. We're now bringing it down to about 1/8 of a millimeter. Do the same for the minimum width, that can also be real tiny, and same for the thermal clearance, that's fine. The thermal spoke width, this is kind of a weird thing. So the thermal reliefs, I guess you can think about it as electric components obviously get hot. So here, like these ground things up here, you can see this big X cross thing going through it. That is the reason there are several connections instead of just one connection there, is to help draw heat away from it. So those are your thermal spokes, I guess, is what those are. So this is this is thermal spoke width. That's the width, essentially, of these things here. Those are actually fine being big. That's not causing us any issues. We're going to leave those at their default 0.5 millimeter. And then I'm going to click OK. And now you can see, whoa, that's gotten much closer to things now. And in fact, it's filled in much more of the board. There are still some places it can't quite reach, like there and down here. But also, none of those places are places that have ground connections in them. So we've managed to fully connect everything here, which is really good. And I think it looks really cool. I think PCBs look really neat like this when you put in fill layers. If, though, you do get sick of seeing fill layers, on your display options here on the left, you can, the first one is show filled areas in zones, so that's showing the filled areas. If you go down one, it's do not show the filled areas, so the filled is still there, but it's just invisible now. Or you can show basically all of the borders surrounding filled areas. This one's a bit of a crazy view. It's kind of difficult to look at, if I'm being honest. So I would either go with don't show the fill at all or show this one. But hey, to each their own. Awesome. That is just about done, actually. And so you can see here, of course, if I zoom in, for things that aren't supposed to be connected to ground, like 3.3 volts, it's constantly surrounded by this minimum amount of padding. And that's actually what we configured a second ago. So you can see that's totally fine. That's not going to get shorted out, but this ground pin here, you can see it has these big spokes going into it, so that's connected to this big filled area. But everywhere else is very neatly cut out, all of these little margin places. So here's another ground thing, so that's connected into the thing. Here's a nice big cutout for our 3-volt power is running through this like little tunnel almost inside of the ground plane, which is kind of cool. Nice. I've intentionally left one mistake for us to catch here because PCB new, like the KiCad thing, has a rule checker. So if we click on our lovely little ladybug, it can check to make sure we're not doing anything silly. So if I go ahead and click run digital rules check, or design rules check actually, I think is what it is, we get no big problems, but it does say we have some unconnected items. So it says here, well, it looks like you haven't connected this reset to this other pad. So if I click on that, you can actually see it kind of brings us to the place where that error is, if you will. So I guess if we zoom in and scroll away, like, oh, where is that? And click it, it'll take us there, which is cool. So it's these two reset things that need to be connected. Now, in the real world, will this PCB work? Yes, because the way these buttons generally work, if you dealt with them before, is basically inside of the button itself, these two reset lines are connected. So when you press the button itself physically is going to connect these two things. You don't need to on your own. Well, actually, it won't. So what the button does when you press it, is it connects both of these ground pins to both of these reset pins, but just like either one of these could be connected to either one of the others. Everything on the top half gets connected to everything on the bottom half. So the bottom half is always actually connected to each other. So these reset lines, they're already connected by the button. Ground lines are already connected by the button. But if we want to get in good habits and connect everything that we can on the PCB, just so we don't ever mess up in the future, we can always do that. So I'll go ahead and click X, draw a new trace over there. Of course, our outline is wrong, but if we click B to refill, you can see it cuts out a nice little place for us there. Now if we run the rule check, we get no problems, no unconnected items, and our board is all set up just about. At least electrically. So I'll give it a quick pause there, and I'll ask how people are doing, and then we can do a bit of silkscreen tweaking, and it looks like, actually, because I was planning on the session being over now today, because I thought our AGM was today, because I'm not terribly clever sometimes. But since our AGM is next week, we have a little bit of time, so I might even show you people, if you would like, how to order PCBs on JLC PCB, how you like export it from here, if that makes sense. Cool. Before that, though, any questions? How are people doing? How are people feeling about fills and connecting stuff up? Any questions, comments, feedback, life concerns? Dun, 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 dun. Awesome! A thumbs up. I'll take what I can get. Cool. Philip is either pondering a very deep question or an excellent joke. So I will give him a second. Dun, 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 dun. He is good. Okay, awesome. Coolio. In that case, then, let's vibe on to do some silkscreen. So, to focus on the silkscreen, no worries at all. To focus on the silkscreen, what we can do is turn off our copper layer visually. So over here in our layers, we can just click the little check mark for FU copper. Oh, maybe not FU. It's actually F.cu. Whoops. I didn't mean to be so aggressive there. Yeah, F.cu front copper. Cool. Point is, we can turn that off. With that off, we can see what's going to be on our PCB itself. So the purpley bits are solder masked places. So what that means is that they are places for you to solder to. Same with this little gold contacts and pads. So those are going to be exposed. The rest of the things are going to be covered in like a nice silk screen. But all of these teal letters and things, they probably won't be teal in the final product. You can pick what color they are, I think, depending on the PCB manufacturer. But those will be on the thing. Those will help us know, like, okay, which capacitor, for example, is this supposed to be? So we can check our design and say, C2 is a capacitor that has... C2 is a 1 microfarad capacitor. So we can check that in our schematic, and we can solder a 1 microfarad capacitor in that location. But for some things, like, for example, our power regulator, its label is inside of something else right now, so that's kind of ugly. So what we can do is fix up our silk screen just by grabbing things, moving them about. I want to do 0.5 millimeter grid, just so I can snap things a little bit, but can move things decently flexibly. I want to put our microcontroller thing in the middle here, actually, because remember, these are most important for when you are soldering things on. Once things are soldered on, you usually don't need to see these references very often. So it's fine to put it underneath the part itself, because we just need it when it's not there. This one here, hard to say actually where I want to put that, because I want to do something with these ones here. I think I'm going to move for our GPIOs, them down to the bottom. So there's one at the bottom. White courtyards, are those going to be an issue? No, they're not. They'll be fine. Yep. So we can move those down. Those are. This one I'll keep here. I'll rotate it so you can actually read it on the board. Doesn't actually matter, to be honest, because you can rotate a board, obviously. So I'll put that one there. That one's fine. This capacitor could be a little bit clearer. I'll move that down to the left side of it, so it's not in the way. Diode here. I'll make that one sideways, actually. Will I? No. Twice now I've decided to do that and then decided against it. I guess the direction it going this way implies that the part it's labeling also goes this way, so it makes it a bit clearer maybe. When I'm putting it on top, though, I will rotate it. This is entirely personal preference, so don't worry, there's no science to this. This silkscreen has zero functional effect on the PCB, but you do want to make sure that it is legible, unless you want to play guessing games when you're assembling it yourself. So there we are. That's fine. All we have is that weird one there. Go ahead and grab that. How am I going to sort that one out? You're going to be a challenging one, aren't you? I've not left myself enough room for that, to be honest with you. So I'll put it up there. Remember, overlapping with the white lines is fine, because the white lines don't actually get printed on the board. And I'll move that up there a little bit so it's a bit clearer. That is that resistor. Well, that's hideous but legible, I guess. For consistency, I'll do... Oh, that's rude. Okay, I need to decrease my grid size. We're going to go to 1/4 millimeter now. There we are. And rotate that around. Yeah, no exact science to that. Would you agree that's tolerable? I don't know. What do you think? Anything that you'd like to tweak around there, or is that a tolerable enough silkscreen? Save. Well, nobody's told me it's disgusting out loud. Excellent. Looks legible. That's what I'll take. Neat. If you're feeling fancy, I think you can also import graphics again. You can import into your silkscreen layer, like cool graphics. So something that... so if you want to put like a logo on here or some text, you could just export that as a DXF somehow. I would actually, for that, recommend... Yeah, we got time. Oh, whoops. That's my Inkscape for something else. I'll open a second thing of Inkscape. If you've not played with... I feel like we've seen Inkscape before, actually. I think we've seen it for... That's brought me back there again. I would like a new window, please. Oh, it won't let me open a new window that way. Okay. I will open a new window on my own terms. New. That has done what I wanted. Well done. Okay. So I think we've seen Inkscape before, probably for when I was talking about laser cutting. Yes, exactly. Fantastic. So here we could design something if we felt like it, you know. Pick a cool bit of text or something for Bionics, so we could like take in the Sheffield Bionics logo or something like that. I won't show off like graphic design stuff necessarily here, but the point is, if you wanted to put like some text and nice font, maybe I like a font called IBM Plex, and that's some weird version of it. So we could do like Bionics or something. And we could have like version 0.0 or 0.1 or something like that. You know, do some text alignment, pop it in the middle. Not an Inkscape tutorial, I'm sorry. Ugh. But there are lots of excellent Inkscape tutorials. But then the point is, you can grab something like this, and you can say, save as, and put it in the place where you'd like to. Well, point is, here you can go down to the options, the outputs. One of the options is a DXF. So you can pick a DXF, you can save your designs as DXFs. I think we had to do that for laser cutting as well. And then those DXFs you can import into our PCB just the same way. I don't actually think this will fit anywhere on our PCB, if I'm being honest with you. So I won't bother. But do know, if you ever do want to design graphics, or convert graphics even, if they aren't DXFs already, you can import a lot of things into Inkscape and put them over there. You can even do one thing I'll show off just in case people are intrigued by it. I have no idea what that is. What is this? This is a weird logo, I think, for, yes, a bizarre project we did about rainbow-colored sheep. Point is, that is a pixelated image. That's not something we can easily convert, but there's a lovely feature if you go to Path, Trace Bitmap. Single scan, how's that look? Awful. Auto trace, how's that look? Much better. Okay. And... but okay. So you can pick like thresholds, or maybe you want to do multiple scans. There's lots of different settings here, obviously. Smooth corners optimate. But the point is, if you play around with that enough, you'll eventually get this here, which is an overlay that's something that you can export as a DXF, because that's a scalable vector graphics thing. So that's how you can get DXFs exported even from images like that. So there you are. There's a brief detour if any of you are going to be PCB graphic designers. Awesome. Yeah, one last thing to do, and that is to put the screw holes in this thing, I think, because I totally forgot to do that. So if we take a look at our copper, for example, you may notice the copper fill entirely covers our pretend screw holes that we put on there. Because remember, the user layer doesn't actually do anything. It's just there for our personal reference. So we're going to use it now as a reference for the real thing. So I'll turn off the copper fill again. And what you can do is under place, I think. Yeah, place and footprint is an option. Or you can use the keyboard shortcut O. So just press the O key. So I'm going to press the O key. I pressed the 0. I was already doing that wrong. Okay. So I press the O key. You can click. Wow, you can pick any footprint in the world that you're feeling. I want to do a screw hole one though, so I don't actually know if it is. Oh, whoa, really? Hold on. Hey, that's really neat actually. Off topic, those are keyboard switches. So if you want to build your own mechanical keyboard, now I can design my own PCB for that. That's built in. Didn't even know. Well, now I know. I was looking though for screw holes, of which aren't directly called screw holes. One moment, let me check my notes to figure out what they're called. Because it's a very specific footprint. That's what they are. Test points, I think. Test point. But there are different types of test points. Test point pad. That's a plated hole. That's what I was looking for. Plated holes. There we are. Yes, that's just a little hole surrounded with copper or a bit of metal. So better to tie your screws into. That way they're not just scratching like the surface of the board. This also ensures that no traces can run through this metal hole, and that will prevent any of your screws from ever touching things they electrically should not. So go ahead and grab that. That's a 2mm one, and we'll go ahead and place that up in here. So now this again is one of those lovely eyeball-ish processes. Also, there's a silkscreen layer here. It says ref and then a couple stars because it's missing the reference because it's not part of our schematic. So it does not know what this part is, but that is fine because this does not need to be connected to anything. If you want to get rid of that, you can go ahead, roll over the ref, press E, change the layer it's on. So here's a big layer drop down. It's currently on the front silkscreen. We'll move that to be on the front fab layer. So f.fab. That is the one that we have hidden currently, so I'll click OK. It disappears, but of course it's still there on our kind of information layer there. Cool. So now it's just a matter of placing this. I'll go again down to 1/10 of a millimeter. Go ahead and grab it, and we try and line it up best we can. I think that's about right there. That looks like it's leaving a nice consistent space on that side, and if we click off of it, well, if we click on user one, there we are. Now we can see our green circle above, and that looks pretty centered in the other thing there. So that's pretty well aligned. We can now do something. We can click on it, press Control D for duplicate, and then go ahead and drag that and do the same thing in other places. Is that in the right place? Ooh, in fact, this is interesting. This is going to cause us to redesign things a very, very, very tiny amount, probably. So that's fine there. Excellent. We'll do another Control D for duplicating it. Zoom right on in. Go ahead and place that there. If I'm being honest, I'm going mostly off of the way it fits into this corner more than the thing hidden behind it. But again, of course, it is in the middle of the thing, so that's fine. Grab there and place there, I reckon. And click off of that. Nice. Oh, that's pretty good. So now what we can do, first of all, flip back on our copper so we can take a look at it. Yikes, that's a disaster. Well, is it? I don't know. The copper is touching that and probably shouldn't be. So if we go ahead and press B, refills it. Now it's not touching it, which is excellent. So refilled our thing. We can run our rules check again. So whip out our ladybug, press run digital rules check, and aha, yes, that's what I thought it was. So courtyards overlap. Between this footprint here, which is the thing we've just added, and our resistor 1. So this is the thing I said we might need to redesign, because if we turn off copper and look really closely, dun dun dun, they're touching each other, and that's not great. There won't be enough room for like the resistor, for example. So this gets a little bit annoying because we'll have to redo a couple of traces, but it's fine overall. So I will grab this resistor and move it a little bit. I'm going to move it down there. I think that'll be fine. So that's now no longer in the way. Not touching that anymore. We can double check by doing a rules check. Looks great. But now, of course, as you may be sensing, that's looking a bit strange there. Amazingly, it's still touching things properly. Regardless, I'm going to redo these traces. So if I roll over there, press delete, roll over here, press delete. I can now reroute the traces a little bit nicer, perhaps. I would kind of, well, you know what? Do what you like, KeyCAD. I won't tell you how to live your life. I will run that one the other way, though, because I do want to tell you how to live that part of your life. We can do B to refill, and yes, that is honestly fine. Cool. And then we can go ahead and check our Ladybug Boy digital rule check. No problems. There's an unconnected item now. How is that? Oh, that's incredible. Fascinating. So, remember a second ago when I said that this was fine. It is not fine. Check out this. Those don't touch each other. That means this entire plate inside of here is not actually connected to ground. So, once again, goodbye, trace. And we're going to remake you, except you're going to go up this way that time. And I'm going to hit B to reflow. There we are. Now, big connection in between those. Press our Ladybug. Run it. No problems, no unconnected items. All done. Our board is finished. We have a nice bit of silk screen. All of the copper plating's on correctly. Screw holes are in. The end. Well and done. Okay. We'll have a bit of time, probably, to do ordering of things. But before we do that, questions? Thoughts? Concerns? You can see why the digital rules check, the little ladybug, is very helpful, because I did not see that cut off the only access between these two parts of the ground plane. So be sure, before you order PCBs, that things are passing in the rules check. Nice. How often would you make these in ARM like BCI? Well, the answer so far to that question is we've not done many of them. At least not... Well, the ARM does have one. That's something that one of the people who actually graduated a couple years ago, I think, designed. It's a really nice motor driver board, does like PID control and stuff. That whole fancy board he's designed and has made as a PCB. And that's used in the ARM project for driving, I think, the motors controlling fingers. Leg, I'm not sure if Leg is using any of these just yet, but they might be soon. BCI, you have a headset already with most of the things that you need. However, you can make your own electrical sensors as well, which is what, for example, Shinsuke has done for the ARM project. Although it could also maybe be a BCI sensor, I'm not sure if it's sensitive enough. But he's made his own PCB for that. Basically, these are for whenever you have a lot of breadboard electronics that you would like to no longer be breadboards. We don't have too many of them yet, but that's kind of why we're trying to teach people these skills so more people make them, because breadboards are really great to experiment with, but sometimes a bit fragile and could certainly be more compact and easier to fit inside of like a design if you have an actual PCB like this. But yeah, good question. I think with the new ARM they're building, there's going to be quite a few of these PCBs in it, but it might be worth double checking with them. And Leg Team, I assume, actually will definitely be using these at some point. I'm just not sure where they're at actually at the moment, because it's been a little while since I've caught up with them. But yes, good question. Dun, 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 dun. Cool. Any other questions? Yeah, no worries. Happy to provide a little bit of info there. I wish I could provide you a bit more of it, but hey. Doing my best. Awesome. Okay. Nice. If there are no questions, then we'll do, or no further questions. If there are further questions, feel free to smack them in the chat. But I think we'll go ahead and look at how you might order one of these real quick. So, like I said a second ago, JLC PCB is the one the manufacturer will be using. So, hello, friends. I'll go to their homepage and see if that's more helpful. I'm also really zoomed in and it's stressing me out, so I'm going to try 150% zoom. Whoops. Oh, well, all right, there we are. So you can get a quote, or there you are, 2-layer thing. You pop into design, I think. So, we've done our final rule check. We know that this board is good and sane, so now we just have to export it, basically. So JLC PCB, different manufacturers require different things. JLC PCB requires that you have Gerber files. So to generate those Gerber files, you can go up to File. Well, first make sure you have everything saved. You go up to File, and then there's an option here for Plot, like you're plotting a graph almost. So if you go to Plot, whole bunch of things here. Basically, this can be left at default, I'm pretty sure. Let me think about it. Yeah, I think that's fine. So this is fine default things. You can pick an output directory. So this is where you want it to go. I'm going to keep it just in this folder. That's fine. Sure, that's fine. I was just asking if I wanted to use a relative or absolute path. I have no idea why it asked me that. Doesn't actually matter all too much. Actually, saying that, putting that there, I'm going to actually put that in its own folder. I'm going to create a new folder called Gerber and send it there. Nice. Cool. Rest of that's fine to leave it default, so we can go ahead and smack the plot button. So that's done. It's giving us green output messages, so that's fine for us. And then we'll also need to generate some drill files. So these Gerber files kind of tell the PCB manufacturing plant, here is where traces are laid out, here's where components are, and then this drill file says, here's where you need to drill holes in this board. Again, all the defaults here are fine. Go ahead and click on it, then smack generate drill file, and you are all set up, I believe. Oh, actually, maybe not. So one thing we do want to do, since we've designed our board, I guess, in millimeters here, is we want to change drill units to be millimeters instead of inches. I think this depends on the manufacturer you're using. So if you upload it, the manufacturer usually gives you a preview of what they think your thing looks like. And if what it looks like looks wrong, then you know, okay, I need to go fix something. But millimeters it looks like from tutorial things. Awesome. So Gerber thing, all those are in the Gerber file. Now also to upload this, because there's a whole bunch of different files, they need to be zipped. So I'm sure there are different ways to zip files on different operating systems. But for me, on Linux, I can just vibe on into where I've just put everything, which is very far away. Societies, Bionics, Bootcamp, PCB, Tutorial Vibes, Bootcamp, and Gerber. There we are. So this is the thing I need to put in a zip file. So I'll right-click on that, and I can click compress, and then just do zip for myself. If you're on Windows, I think zipping is built in automatically, probably on Macs as well. If not, you can download something like 7-zip. That's an easy program for this kind of thing. Anyways, once it's a zip file, we can now go here. We want a 2-layer PCB because, well, essentially we're only using 1 layer of copper. We have traces on the front, and that is all. This would also allow you to have traces on the back if you wanted. 4 to 6 layers means you have traces inside of the board, which is very fancy, and you can also do like assembly stuff here, or stencily things, which is just parts that don't actually have electronics on them as far as I understand. Cool, so what we want to do, click the quote now button or whatever. I think this lets us upload our thing. Yeah, add a Gerber file. It only accepts a zip or a RAR file, so if you can if you can compress it into a RAR file, that'll work as well, but I'll just upload gerber.zip. It'll go ahead and do some stuff. It's processing our files. Oh, I have uploaded the entirely wrong one. Well, congratulations. You've all seen the file that, it was one of the earlier prototypes, I think, of the EMG board. So this is the one that Shinsuke designed for the ARM team. I didn't even check the folder I was in before I submitted that. Yeah, I'm in my downloads. Terrible place to be. Okay, let's try again. Going back to University Miscellaneous. Societies, you know what I ought to do is create a shortcut to this folder. I think that would be the intelligent thing to do. And yet, here we are. Okay, that's the Gerber zip I want. Okay. That was very confusing there for a second. Hey, look at that. That looks pretty good to me. I think that looks like what we designed. What do you guys think? That's the front of it, that's the back of it. Looking pretty. You can see the bits where like the fill aren't, well, where the fill isn't, it's a slightly different color. It'll be that way in real life. It won't be quite as noticeable as this, but obviously that's fine because we've already checked out on all the rules. Our silk screen, there it is in white, very pretty. We can change our PCB color. Does it show that? Yeah, you can make it blue or black or red or yellow. But they've also said this takes 2 extra days, so, you know, pick what you're interested in. Surface finishes, you can pick the type of solder. You might want to do lead-free things sometimes. Is that more money? It is more money. Yeah, I don't know. Sometimes you'll have to do that to be compliant with things. We really don't need to worry about it. Here's why I said you can pick the lightweight copper or double copper thing. We designed for the lightweight one. Rest of the default stuff is fine, honestly. So basically, there we are. That's our board. We're going to get 5 of them, and you can get 5 of them for £1.44. Now, the only issue with that, of course, is the shipping costs. So here, actually, is surprisingly fine. Yeah, great. So the UK itself seems to have a special shipping channel. So that's only, you know, £3.83 to send over, which isn't bad at all. If you make them bigger, sometimes it'll be harder to send over. You can get a whole bunch more PCBs. If you want 150 of them, bam, there you go. Only costs you £10 or 14, I guess. Point is, PCBs are very cheap. The components to put on PCBs are less cheap, but usually still pretty inexpensive. But yeah. So there we are. GLC PCB is a great, cheap, easy place to do them. That's the lowest cost I've been able to find anywhere. I've heard the same from other people. Awesome. Any questions? We're just about out of time, so speak now or forever hold your peace until you send a message elsewhere, and I'll eventually get back to you. So speak whenever, but now is a good time. If you have any questions, that is. Cool. The crowd goes wild, typing questions or pondering. Anything else you could have done to the PCB to improve it? Yeah, so that's a good open. Do you mean on here, the JLC PCB, or do you mean in the design itself? Design itself. Yeah, so there are definitely things you could do there. I guess for this particular one, it's a very simple board, and we've hooked it up in a very simple way. With these components, we've probably done it about as well as you can do it. For some other boards, though, you want to make sure that your traces are very clean. They're pretty clean here. Ways that you could improve it maybe would be using... Well, okay, so here's a good example, I guess. I'll save that, and I'll whip out my one and only cool thing I've ever done, which is the motherboard for the Mini RRV. Hello? Did that open? It did. Yes, so here. One important consideration that we didn't talk about at all today is power and how much power you're running through things. You need to have different sized traces. For example, this board requires quite a lot of power coming down these 2 power connector lines here. So this massive line here is a really thick connection. It's 12 volts that goes into the power regulator, which is actually around here somewhere. But that needs to be really thick because this has a bunch of LEDs that are going to draw a whole lot of power running at full capacity. If that was drawn as a normal thickness line, it would burst into flames, probably. So that's an important consideration, is to make sure that things are correctly sized. To do that, the best tool is also built into KiCad, and that is this little calculator here. And this has a whole bunch of things you can calculate with it. For example, this is track width up here. So you can pick how many amps you're going to run through it. So we're running 5 amps. We wanted to, at most, get 10 degrees hotter than room temperature. The conductor length, say, so 20 millimeters of distance. Resistivity, we'll leave it default. It's just copper, I assume, by default in there. And then you can well, it spits back out here, basically, the width that your tracks need to be. So if we want something that carries 5 amps and doesn't get any hotter than 10 degrees above ambient, then we need to make sure it's at least 2.7 millimeters thick. Well, wide, rather, and then this amount thick. So that's a really good thing for calculating that. It also has a built-in thing for calculating regulators. That's kind of cool. As well as a whole bunch of other nice things. Translines, those are like wireless stuff, I think. Same here, radio frequency attenuators, color codes for resistors, boards classes there as well. So those are some other things to keep in mind. Is if your design requires lots of power and stuff, you might need to get a bit more creative. But for our design, if I'm being honest, I think aside from putting maybe a silk screen on the back to look cool, there's not too much to do with this particular tiny PCB. So I think that's probably about as good as you can make it. You can always shuffle things around to be in better places, though, if you'd like. So yeah, it's an iterative process, I guess. You could order some, see if you like them, and if there's something you want to change, you can do so. That was a very waffly way to answer that question, but maybe it was helpful. Wonderful. Cool. Nice. I have technically dragged you all here for 2 minutes longer than I said I would, so we're slightly over time. So I will send you a feedback form so you can roast me, and then I think let you all get on with your lives. Yeah, okay, yes, gotta go. No worries. See you around, fill in the form if you get time. And yeah, it was lovely to have you both. All right, see you as well, Maria. Nice to have you along.
Great, thank you very much.
Happy to help. Yeah, see you. Awesome. Cool. I would like to... Oh, I can leave or end the call. Fascinating. Aren't you excited recording goers who get to sit here and listen to me ramble? Look, welcome to infinity. Goodbye.